kinematics of 3D manipulators. Okay, so what we're talking about is this is a manipulator, and this is the gripper, and that gripper has to be in some point in space at some precise location so that it can actually grip onto some objects, maybe lift boxes. Now in 3D, the position of an object in 3D space is given by 6 numbers: xref, yref, zref, and then it will also have an orientation. So let's just say that there is a x, y, z for the orientation. 6 numbers. There are 6 numbers which quantify an object in 3-dimensional space. There's a position and the end effector. Okay, so the question is, if you want a manipulator to put an object in 3-dimensional space with any orientation you want, then the manipulator itself has to have some properties. You need at least at least 6 joints or 6 degrees of freedom in order to be able to put an object in 3-dimensional space. So when you look at manipulators, if you buy manipulators or look at industrial manipulators, you'll see that they'll actually have only 6 joints. Some of them have more than 6, maybe 7, but adding a joint makes it more expensive. So most of the time they limit themselves to 6 joints. Okay, so what we can do is, now that we have a technique to figure out the forward kinematics, we can actually, so we can assign coordinate frames. So once we are given a manipulator, we can assign coordinate frames, which we've done. We've created the DH table. And then we can assign, we can compute the position of the end effector. So HN0, H10, H21, so on till HN n-1 is Rn0, Dn0. Okay, now this part, as I said, holds, we need, for inverse kinematics to work, this should be at xref, yref, zref, right? So that is an easy assignment. You can just match that up, but it's less clear how you can do with the rotation matrix. It's going to have basically numbers like this: 2, 1, 2, 2, R2, 3, R3, 1, R3, 2, R3, 3, and somehow we need to relate this to what we had: phi ref, theta ref, and psi ref, right? How can we relate 9 numbers to 3 numbers? Because rotation matrix is a 3 by 3. So we need to do this. And the way we do this is, it was actually one of the homework questions in the previous homework. Once you figure out H and do the calculation, the rotation matrix would look like this for a 3, 2, 1, right? And we need to now, so this is how the nth Rn0 would look, right? We just parameterize the coordinates or the orientation of the end effector using phi, theta, and psi. So this comes from 3D rotations. But that can be true for any end effector, right? So we just set it to Rn0. And so what we do is, we now have R11, R12, R13, R21, R22, R23, R31, R32, R33. these are only going to be 3 by 3 numerics, right? It's going to be a matrix of numerics. When you do this computation for a manipulator for given angles, it'll give you numbers. But we need to convert these numbers to angles. How do you do this? Well, what you can do is you can take the easiest route. That is, each of these elements in a row column will match with the row column in that rotation matrix shown there. It looks like the first two rows are pretty complex. We can actually use only the last row to compare. So what we can do is we can say set R31 equals minus sine theta, because that is R31. So from that we can compute theta, which is theta ref is sine inverse R31. So we've computed this now. Next, we equate R32 with cosine theta sine phi. And because we know what phi ref is, sorry, what theta ref is, we can compute what phi is going to be. Phi ref is sine inverse R32 divided by cos theta ref, where cos theta ref was found here from here. We solve for theta ref before we solve for phi ref. And then finally, if you want to compute the angle psi, okay, there's a problem here. There's no psi here, so I can't really use. Yeah, I cannot use. I can only compute phi ref theta ref, because if I use this is redundant. I need some expression here which has psi. So maybe I could use these two. You could use either one, right? Make a choice which you want to use and then use that to solve for psi. So using that, the highlighted one, we can, let's use the first one, see. So we have R11 is cosine psi cosine theta. So I can solve for psi ref as cosine inverse R11. So I need to divide by cosine theta ref. And I know cosine theta ref because it's been computed before. So this is how you could get theta, phi, and psi by looking at the rotation matrix. Okay, so this is not new. You've done this in a homework problem. Now let's put this all together and solve inverse kinematics problem for a 6 degree of freedom manipulator. I've spared you the trouble of computing the DH table. I give you the DH table. No, I don't need to do this. Oh my God, I lost. This manipulator was developed in Stanford, and so it's got the name Stanford Manipulator. This is the assignment. Well, this is how the manipulator looks clearly, but this shows how to set the DH table. But what you really need is this DH table, right? That is the key to animating it. So once you have the DH table, the question here is, so compute position orientation of end effector, which is kind of straightforward to do because you're given the DH table. Animate the manipulator. And then finally, compute, right, given position / orientation of the end effector, compute the inverse kinematics. Okay, so for step 1, which I need to compute the position oriented in the end effector, it's simply setting up H60, which will be H10, H21, H32, H43, H54, H65. Where do these things come from? All these things comes from the 6 lines in the DH table. So each line would give you alpha, D, theta, alpha, A, D, and theta. So you can basically compute each of these H individually, and then you multiply them to get H60. So this matrix here will have R60, D6001, and the position is D60, and the orientation is embedded in here. You can use what I showed you earlier to compute phi, theta, psi. You expand out R in terms of phi, theta, psi, and then compare the 3 of those elements. So this cannot be done by hand. So what I'm going to do is I'm just going to show you code which basically does part 2 and part 3. Part 2, we've already seen how to do it. You just have to do position of, you need H10, H20, H30, so on to basically plot the joints and just draw lines between the joints. And the third one, to do the inverse kinematics, we can do what we did in the previous class, one inverse kinematics, where we used fsolve to solve for the roots of an equation. Okay, so let's run this. Control Shift P. Okay, so this is basically showing the manipulator, and the dot is where the manipulator end effector should be, the last link of the red, and then you can actually visualize this in 3D. Okay, so this tip should be here, and really here I'm not doing the inverse kinematic. This is just the initial position. And now what I need to do is I need to do fsolve and try to put this end effector there. So that's the next step. So I'll close this. I'll comment this part out and then go here. So this is fsolve. Okay, so there is an initial guess, which I think is this one, x0. I use fsolve inverse kinematics as my function. And then I just do Control Shift V to run this. And then now you can see that the tip of the red is actually at the black dot. That is where I want the end effector should be. You can't quite see the position orientation because I really did not have a gripper there. But based on the inverse kinematics solution, it seems that the it's actually, see, it's probably fval. If you look at fval, that tells you how close you are to. Oh, I did not print it. Let's print fval. Fval is the result of fsolve. So if all of the elements are 0, that means it actually reached its position. Run this. You can see fsolve is 1e -7, 1e -7, just 1e -7. So it means that it achieves the position orientation it was told to achieve.